Welcome in question number 15, and this question also has more than one correct answer. And question is in an experimental setup to study the photoelectric effect. A point source of light of power 3.2 milliwatt is used. The source emits monoenergetic photon of energy 5 electron volt and is located at a distance d equal to 0.8 meter from center of a stationary metallic surface of work function 3 electron volt. The radius of a sphere is 8 millimeter. Assume that the sphere is located and photoelectrons are instantly swept away after emission. Also assume that the efficiency of photoelectric emission is 1 for every 10 to the power 6 photons. In the present setup, we have to determine the de Broglie wavelength. In second option, as we know that the answer may be more than one, so we have to try for all options. In first option, we have to determine the de Broglie wavelength. In second option, we have to determine the charge on sphere just when the electron emission stops is this. So we have to determine this electron emission charge just when the electron emission stops. And in third option, we have to determine the time after which photoelectric emission stops is nearly 111 second. And in fourth option, we have to determine the light source emits 4 into 10 to the power 15 photons per second. So first we try for option number 1. So we determine the de Broglie wavelength, and we know that number of photons emitted per second and it should be we know that this is 3.2 milliwatt. So power is 3.2 milliwatt, and we can write 3.2 into 10 to the power minus 3 watt and divided by 5 into 5 energy of electron. Energy of photon is 5 electron volt. So divided by 5 electron volt, and we can convert it into joule after multiply by 1.6 into 10 to the power minus 90. So it becomes 4 into 10 to the power 15 per second, second inverse 1. And energy of fastest electron, it should be fastest electron, it should be 5 electron minus the work function is 3 electron volt. 5 electron volt and work function is 3 electron volt. So 3 electron volt should be subtracted. So the electron which emit from the material, the energy of that electron should be 2 electron volt. So de Broglie wavelength of fastest electron it should be lambda is equal to under root 150 upon V. And if there is energy of fastest electron is 2 electron volt, so voltage should be 2 volt. So it should be 150 upon 2 volt, and it becomes under root 75, or near about it should be in angstrom. It should be at 8.7 angstrom, near about 8.7 angstrom. So if we see option number 1, the de Broglie wavelength of fastest moving photoelectron is nearly 8.7 angstrom. So option 1 is correct. As we know that there may be more than one option, so now we will try for option number 2. So for option number 2, we calculate the electric potential, as we know that the potential of positively charged sphere will become 2 volt and fastest electron will also return to sphere. So V equal to, it should be 1 upon 4 pi epsilon naught Q upon R, and it should be 2 volt. It should be 2 volt. So Q is equal to, this Q is equal to 4 pi epsilon naught R into 2. 4 pi epsilon naught R into 2. Or we can write 8 pi epsilon naught R. And we can write, as we know that it should be 8 pi epsilon naught, and what will be the value of capital R in question? This is 8 millimeter. Capital R is 8 millimeter. So we can write value of R 8 millimeter means multiply by 10 to the power minus 3. So it becomes 8 into 8, 64 pi epsilon naught into 10 to the power minus 3 coulomb. This should be the charge. So if we see the option number B, it is observed that after some time emission of photoelectrons from the surface of metal sphere is stopped. The energy on sphere just when the electron emission is stopped is 64 pi epsilon naught into 10 to the power minus 3. This should be the charge. This should be the charge. So we have determined charge, and so it is proved that answer B is also correct. So as we know that more answer may be correct, so we will try for option number C. So option number C, we know that the distance, suppose distance from the sphere is d, and d is very greater than capital R. Capital R means radius of the sphere, and the photons are emitted uniformly in all over the direction. So photons will fall on cross section pi r square. The photons will fall just like that. This is the radius. We can consider R, and area of this cross section is pi r square. So number of photons falling per second on sphere, it should be number should be 4 into 10 to the power 15 this. So 4 into 10 to the power 15 divided by 4 pi d square. Suppose this is source and this is a distance d. So suppose it represents a sphere. So divided by 4 pi d square, multiply by cross section, area of cross section pi r square. So it becomes 4 cancel out, and 10 to the power 15 pi cancel out, r upon d whole square, and we can write 10 to the power 15. R means 8 millimeter, 8 into 10 to the power minus 3, and d is 0.8. So it becomes 10 to the power 8 cancel out, 10 to the power 11. 10 to the power 11 second inverse 1 per second. So number of photoelectrons emitted per second, it should be 10 to the power 11 upon 10 to the power 6, 10 to the power 5. 10 to the power 5. It is given in question. Assume that the efficiency of photoelectric emission is 1 for every 10 to the power 6 photon. So it becomes 10 to the power 5. 10 to the power 5. Now charge developed per second. It should be 10 to the power 5 into coulomb charge or electronic charge 1.6 10 to the power minus 19 coulomb per second. And time required T, it should be we have determined the charge, this 64 pi epsilon naught into 10 to the power minus 3. So 64 pi epsilon naught into 10 to the power minus 3 divided by 1.6, this charge developed per second, 10 to the power 5 into 1.6 into 10 to the power minus 19. So it becomes 4 pi epsilon naught into 10 to the power 12. Or we know that 4 pi epsilon naught is 1 upon 9 into 10 to the power 9. So 10 to the power 12 upon 9 into 10 to the power 9. So after solving it, it becomes 10 to the power 3 upon 9. 10 to the power 3 means 1000 upon 9. If it is 10, so answer will be 100. So the answer will be nearly 111 second. And option C. If we see option C, time after which photoelectron emission stop is nearly 111 seconds. So answer C is also correct. And if we see the option D, the light source emits 4 into 10 to the power 15 photon per second. Already we have determined that photon emitted per second is 4 into 10 to the power 15 per second. So answer D is also correct. So in this question, all the options A, B, C and D are the correct answer. All the options A, B, C and D are correct answer. So in this type of question, we have to try all the options. If we know that the answer may be correct more than one, so we have to try all the options. So thank you very much. In another video, we will meet again with another problem like this, and the remaining problem of this paper NSEP 2022 are like this, in which more than one option may be the correct answer. Thank you very much. You can write us if you feel any problem or any doubt.